All right, so let's start with the next topic, which is design of inverters and basic gates in MOS technology. All right, so this is a simple inverter that we have seen. That one of the simplest inverters that we can make is take an NMOS transistor and put a load resistor here and connect it to VDD. The other terminal is ground. And we've already seen that if you take an inverter like this, when you don't apply any voltage or voltage is zero, the threshold voltage that we are taking for a transistor is about 1 volt or 0.7 volt or 1 volt, let's say. So the transistor is off. And so when you apply 0 volts, the transistor is off. This is connected to the supply voltage, we'll take as 3.3. And so the output is 3.3 here. So when you apply a low here, the output is high, is 3.3 here. When you apply a high voltage here, which is same as the VDD, which is 3.3 here, the transistor turns on, and the resistance offered by the transistor goes into linear region where it acts like a resistor, and the resistance offered by the transistor is very small, and therefore by the voltage divider here, you can see that the output voltage becomes very, very low. It doesn't go to zero, but becomes very low here. So when you apply 3.3, you get an output voltage which may be 0.1 or 50 millivolts, depending on how you design the inverter here. So when you apply high, you get a low. When you apply low, you get a high. So this functions like what we expect of an inverter. Now, when we design an inverter, what are the important characteristics we should look for? The first thing, of course, is it should act as an inverter. Fine. That's which we call as the functionality. It should obey the functionality, right? The other one is we've already seen that area is important. And so how much area does my inverter take has a bearing on how much area would my NAND gate take, and similarly flip-flops, registers, adders, and all of that. So they're all related to the area of a basic unit cell here, which is a inverter. And so area is important for us. We are not going to use an inverter under static conditions. We'll be switching. And therefore, when I switch V in from 0 to 1, how long does it take to switch from 1 to 0? Right? So the delay is important. And power dissipation is important. How much power does it draw from the supply here? So that is important. And there's one other parameter which is also important besides area, delay, power that you see here. And in order to appreciate that, let's consider a different inverter here. Let's look at this one here. Note that what we are plotting is V out versus V in. Output voltage versus V in here. Right? So if you look at this one, and the question that I want to ask is this a good inverter? Is this a good inverter? Right? So that's the question that we are asking. And if we look at this one, let's look at it in detail. So let's go back here. And if we apply a logic low, which is 0, if I apply 0 here, I get a 3.3, which is VDD. And if I apply 3.3 here, I get 0 here. And 3.3 seems to work fine, right? 0, 3.3, 0, 3.3, 0. That's what we expect. Low, high, low, high, low, high, right? So this is working fine. Except that I don't have an ideal condition like this. I don't have an ideal condition where my logic levels are, if my logic 0 is supposed to be ground, that is always ground. And if logic 1 is supposed to be VDD, is always equal to VDD. That's not the situation in real life. So what happens is, the logic levels that you see here, they get corrupted. They get corrupted by various sources of noise. All right. At some point, we'll look at where the noises can come from. Now, if we look at our inverter, this inverter, and let's say a noise gets added to my system here. So let's say all these inverters are fine. I get a noise which is added here. So let's say 0, 3.30, everything is working fine. I add a bit of noise here. And the noise is, let's say, 0.2 volt. If I add a noise of 0.2 volt here, this is addition. So I add it here, 0.2 plus 0. So this goes to 0.2 here. And from this voltage transfer characteristics, for 0.2, I can figure out, I go here 0.2 and I look at what is the output voltage. I'll find 3.1. And then 3.1, so I go here 3.1 and I find it is 0.2, 3.1, 0.2. So what happens? If you look at this one, somehow a noise got injected into one of the inputs, a noise equal to 0.2. And what happened to the noise? The noise is propagating, right? So there's a note that the ideal value is 3.3. And what do you have? There's a noise of 0.2 that you added. There's a noise of 0.2 here also. And then the ideal value here is ground. There's a noise of 0.2. And noise of 0.2, 0.2 throughout. So once you inject a noise at a certain point, the same noise is present everywhere. Why? Because we can understand, if you look at this, the gain of this particular one is what? 1. You start from 3.3 and you go to 3.3 and the scale is also 3.3 here. So the gain is 1 of this inverter. So when you inject a noise of 0.2, well, 0.2 propagates. That's not a very good characteristic. For example, now just briefly, for example, where could this 0.2 noise come from? That you may be wondering. Well, as I said, there are various sources. For example, the ground that you see here is not a perfect ground. You know, you may have a ground pin where you get a real ground, and from that ground pin of the IC, the wires are running all over the IC there. And because of currents and all that flowing, these wires have some resistance, so you have voltage drops at various places. And remember, to the ground, there's an element like this connected here. So when you switch something, then there is a current that flows into the ground. The current flows into the ground, which is here. So the ground is carrying various kinds of transient currents. And if it has a resistance associated with it, then there is a voltage drop in the ground also. So there are possibilities of this getting corrupted. There's not a pure 0 volt. This may be higher, lower, and maybe randomly varying depending on what all is connected to the ground. Similarly, my VDD can get corrupted. VDD may also have various kinds of ripples and noise in that particular one. And so anyway, if you recall, we said that all these transistors are made in the same substrate. All N-type transistors share the same P-type substrate here. So substrate is common for all of them. And if you have not made proper contacts to the substrate, the voltages from one inverter can get coupled to the other inverter through the substrate. Substrate is common to all of them. So, something which is not intended for an inverter through the substrate, it may come and start affecting my inverter here. Now, note that if anything gets injected into the substrate bias affects the threshold voltage, thereby affects the currents and things like that. Okay, so there are various, at some other point we'll look into maybe how the different sources can, noise sources can get into the system here. So right now what we are saying is that in a system like this, once a noise gets injected, then the noise just stays here. Now that's not the only inverter where the noise may get in. For example, what about this? Let's say the noise gets in here and here and here. At various other places, noise also gets in. So for example, I could have 0, 3.30, everything is fine. Noise gets injected 0.2. So all this gets corrupted by about 0.2 volts here. Let's say the same amount of noise gets here. It gets added 0.4 here, 2.9, 0.4, and then like this 0.6 and all that. It may happen, you have a long chain of inverters. Or even if you don't have inverters, think of, instead of inverters, some other gates, NAND gates, NOR gates, or whatever. You have a long chain, and at various points, noise gets injected here. Eventually, what will happen is, note that the logic low is getting corrupted from ideal value of 0 to 0.2 to 0.4 to 0.6. Eventually, it may become sufficiently large that you cannot consider it as logic 0 anymore. Right? So you get an error. So a system like this is not a very good system here, an inverter like this. Because why? Once you inject a noise into it, well, the noise just stays there. The noise just stays there. Because why? Because it has a gain of 1 here. So what kind of a system should you look for in an inverter? Suppose you do inject noise, you want noise, what should happen to the noise? What would be a good system here? A good robust system. Robust system means it's insensitive to noise. So what should it do? If I inject 0.2 here, what should happen ideally? Ideally may be completely rejected. So if you inject 0.2 here, and what do you end up getting? 3.3. It rejects it. Or even if it doesn't reject it, what is the other thing that you may expect? Well, it at least attenuates the noise. If you inject 0.2 volt noise here, then maybe 0.1 volt noise is present here. And then the next one, even half, so at least it attenuates it. So what are you looking for? You're looking for a characteristic not with a gain of 1, but what kind of a gain should be there? If it has to reject it, what should be the gain? Reject it. So you introduce a perturbation here, and we are saying this inverter should reject it. No perturbation at the output. What does that, in terms of gain, what does it mean? 0? That there should be a place here where the gain should be 0. Why? Because you introduce a perturbation here. Think of it like a small signal. You applied a small signal voltage, which is 0.2, and you're saying there's no small signal output. That it still stays at 3.3. What does it mean? That the gain is 0. Or if you can't get a gain of 0, so somewhere here, let's say when I'm applying 0 volt here at this point, when I'm applying V in of 0, somewhere here I want a gain of 0. Why? Because it will help us rejecting. If you can't get a gain of 0, at least try and get a gain of which is less than 1. Right? So what we are looking for is, in this case, the gain of this one, del V out by del V in is -1, and therefore the noise persists in the system. Whatever noise you enters, it just persists here. So systems that we want to design, they should be robust in the presence of noise here. Example, as I just said, I inject 0.2 and I get 3.30, 3.3. It completely rejected it. The noise of 0.2 rejected it. Well, look at this particular system here. A flat region here, then there is a region here, and there's a flat region here. Now, flat region means what? So note that normally, where am I? Normally, I'm operating at this place or at this place. Right? When I apply a 0, when I apply input 0, I'm here at this point, 3.3. Or when I apply 3.3 and I get a 0, I'm here. So either I'm at this place or I'm at this place. And at both the places, the gain is 0. The gain of this particular point and the gain at this particular point is 0, which means that any perturbation in 3.3 will get rejected. Any perturbation from here will get rejected here. Right? So one can clearly see here. Or if you can't get this, let's say, then at least if you can't reject it completely, at least you should be looking for a case where in any case, as I said, in this case, the gain is 0 here and the gain is 0 here. So it rejects noise, whether you introduce noise in the logic 0 level, when you add a noise here, or where you add a noise to the logic 1 level here. Logic 1 is normally 3.3. We subtract, let's say, -0.2. We get a lower logic 1 level here. Again, it gets rejected because at both these places, the gain is 0. So the noise gets injected here. Right? A region here and a region here where gain is 0. Or even if you can't get it to 0, you should have a region which is gain less than 1. Gain less than 1 here. Right? In these two regions here. So as I said, normally when you're here, if you apply 0, 3.30, you are in this region here, you add a noise of 0.2. Now when you add a noise of 0.2, you don't get a noise of 0.2 here. Because note that the normal value is 3.3. So the noise that you get here is 0.1. So it gets halved. And then the noise gets halved again. So for 0.1, so 0.05, and then 3.27. So you can see that when the gain is less than 1 in this region or in this region, if you do inject a noise, the system recovers. The system recovers here. Note that as you can see here, this is 0.2. The logic 0 level got corrupted, but eventually logic 0 level becomes 0.05, 0.0125, and eventually it will recover and come back to 0. And similarly, the logic 1 got corrupted, yes, 3.2, but then 3.275, eventually it come back to 3.3. So in order to make robust systems, either we need these regions with gain 0 here, or we need at least a region with gain less than 1 here. Right? Now this is interesting. If you need a region with gain 0 or gain less than 1 here, in these regions here and these regions here should be less than 1. Alright? Then there must be a region with gain greater than unity also. Do you all see that? Because note that you're going from, as you go from 0 to 3.3, the output falls from 3.3 to 0. So average gain of my system is what? 1. Right? As I go from here, this point to this point, I go from 3.3 to 0 over an input range of what? 0 to 3.3. So average gain is 0. Now, if we want a region where gain is less than 1, there must be a region with gain greater than 1. So what we are saying is, to make a robust system, I must have a region which is gain less than 1 here and a gain less than 1 here, in order to make a robust system which rejects noise or attenuates noise. So if gain is less than 1 and less than 1, they must be, that lower gain must be compensated with higher gain somewhere. So what you're saying is, if you want to make a robust system, you will have to make it using an element that can provide gain. I must have a gain in my system in an inverter. If I don't have a gain somewhere, then I can't have a gain less than 1 and less than 1 somewhere else. A higher gain must compensate for lower gain because overall gain is 1. Right? So if you want to build a robust system, what are we saying? You need a gain less than 1 and less than 1 in other regions, and therefore you need a gain more than 1 in some other region. Now, how do you get a gain more than 1? If you want to build gain more than 1, you need a transistor. Transistor gain more than 1, which means an amplifying element. So what you see here is that in order to make an inverter and similarly NAND gates and all of that, you have to make it with an element which can have gain in it. Otherwise, you will not get a robust system here. You will not be able to get less than 1 gain here and less than 1 gain here. That's not possible. Okay? If you go from 3.3 to 0 here and 0 to 3.3, that's how most of the systems work. All right. So with this discussion, what we are saying is, yes, area is important, delay is important, power is important, and let me add a fourth thing a good inverter would be robust in the presence of noise, which means it would reject noise or attenuate noise here. And so we have to study the noise property, the noise immunity of a inverter, and we add a fourth term, performance metric, which is noise margin. Right? And where do we get this noise margin from? You're seeing that this is a property of my voltage transfer characteristics. Different voltage transfer characteristics will have different implications for noise margin, because we are talking about gain less than 1 here, gain less than 1 here, how the noise attenuates and all that. So all those things you get from the voltage transfer characteristics here. So this is, when we design an inverter, this is one of the first things that we do. Whenever an inverter is given, we want to see how does this voltage transfer characteristic look like, right? VTC. What is the VTC of an inverter? And from the VTC, we derive a set of important properties which are linked to the noise margin that is there. All right. Now, before we go into noise margins, let me talk about a property which is frequently discussed, a simple property which is called the inverter threshold voltage. Inverter threshold voltage, let's look at a VTC like this here, V out versus V in, which is given here. Now, what do we mean by threshold voltage? Any threshold voltage, you have an understanding that, so it's obvious that we'll call this as the inverter threshold voltage. If voltage is larger than this, the output is logic 0. If the voltage is less than 0, the output is logic 1. So that's a threshold point. At this voltage, a transition is taking place from logic 1 to logic 0 here. So that's the inverter threshold voltage here. Now, if I have an inverter threshold voltage like this, in some sense an ideal characteristics here, we can look at how much noise can the system tolerate. Suppose we have a VTC like this, and I ask the question, how much noise can my system tolerate here? Okay, so let's put some numbers here. Let's say this is 3.3, this is 1 volt, and this is 3.3. Please remember, for all our discussions, we'll keep VDD 3.3, which is for a 0.5 micron technology, and let's say this is 1. So let's put a chain of inverters. So 0, 3.3, 0, right? How much noise can I tolerate in my logic, on the 0 level here? And still stays as logic, proper logic values here. So, if I note that I have normally 0 this thing. If I add up to 1 volt of noise here, this goes or a little less than 1. So we are still here. And what will we end up with? Getting a proper logic 1 here. So this is what we expect, that if there is a 0 here, we expect a 1 here. And operation will take place properly if I can add up a noise as much as 1 volt here. And similarly, if I add, how much a noise can I add to the logic high? At this point, well, I can add meaning in this case subtract, well, I can subtract up to 2.3. And still my system will work fine here. So we can say noise margin low, how much noise can I add and still my system will work properly, is 1 volt. And noise margin high, how much noise can I add to the logic high level and still the system works properly, is 2.3. Is that a good or bad? Anything wrong with this? Huh? Well, this system, so effectively, let's say if the possibility of noise being there in both logic 1 and logic 0 are equal, then this is not a good design. Because eventually my noise immunity will be determined by the smaller one. My system will fail to work when the noise is of 1 volt amplitude, while 2.3 doesn't really matter. So this is one case. And what is the consequence of this? I mean, what is the reason for this noise immunity for the lower and higher being different? Well, I have asymmetrical characteristics. Well, similarly, I can draw this here, and you can easily figure out here this one. Again, this one has a good noise immunity for the logic low, but poor noise immunity, relatively poor noise immunity for logic high. Again, asymmetrical characteristics. So what should you aim for? When you look at a VTC, this simple example is trying to tell you what. Aim for, if you want equal noise immunity, let's say on the higher side and on the lower side, you should try and build a symmetrical characteristics. All right. So what is the symmetrical characteristics? This is an ideal VTC. So it goes here where V inverter is 1.65, right in the middle. Then the noise immunity on the lower side is 1.65. Noise immunity for logic high is also 1.65. Now, what is the message that it is giving us? One of the simple message that is giving us is that when you design an inverter, maybe this is one of the things that you should aim for. That the inverter threshold voltage should be 1.65. 1.65, why? Half of VDD. So that becomes one of the design criteria. You should design an inverter such that the inverter threshold voltage is 0.5 times VDD here. Now, rarely would you find a characteristic like this. What you would find is maybe something like this here. So how do you define an inverter threshold voltage in this case? So this criteria is fine. It indicates sort of symmetrical characteristics, equal immunity for the lower and higher. So that's a fine, I mean, it's an okay criteria. But how do I define for this one? I don't have a sharp transition. This is what happens here. How do I define inverter threshold voltage? So what we do is we draw a line V out equal to V in and find this intersection. And we call this the V inverter. Right? We call this point as the V inverter. And note that for input voltage larger than V inverter, the output would be closer to 0. So that's why we're calling it threshold. For V in less than V inverter, the output is closer to 1. And for V in larger than V inverter, the output is closer to 0. So in that sense, it's a threshold point. And so for any arbitrary voltage transfer characteristics, if you need to find out what is the inverter threshold voltage, not the transistor threshold voltage, inverter threshold voltage, all that you do is draw a line V out equal to V in, and you get a point intersection, and you call that the inverter threshold voltage. And perhaps in a good inverter design, what are we looking for? An inverter threshold voltage of 0.5 VDD. So that becomes one of the design criteria. Okay, 0.5 VDD inverter threshold voltage. All right, but this doesn't tell us about what the noise margins are. Okay, so let's come back to our discussion of noise margin. Okay. So remember what we are in noise margin. What we are interested in is, of course, how much noise can my system tolerate, and still logically the system should work correctly, right? So if we have an inverter, note that the 0 1s are logical values, 0 1 0 1 0 1 here, and what we are looking for is logical correctness. That in the presence of noise, there should be logical correctness here. Okay. Now, but noise margin is what? Noise margin is defined in terms of voltage. How much noise voltage can I add or subtract from my system? And still it should be logically correct. All right. So what are the steps involved in this thing here? So first thing is, what is logic 0? See, to go to voltage, I have to define what is my logic 0. What do I consider as logic 0? What do I consider as logic 1? And because whatever you consider as logic, for example, if you want, your definition of logic 1 will decide how much noise you can add. So you have to define what is my logic 1 and logic 0. So in a system like this, the definition is very clear. What is logic 1? What voltage would you associate for logic 1? Obviously VDD. There's no other choice. And what voltage will you associate with logic 0? Ground. There's no other choice here. So 0, VDD 0. So that's clear. So when I take 0, 1, 0, 0, VDD 0 here. How much noise can I add? And still, it still works as 1 and 0. Well, VDD and 0, how much noise I can add? We can see here. that we can add up to V inverter. So it's straightforward to calculate what is the noise immunity on the lower side, because there's no ambiguity. What is my logic 0? Well, it's 0 volt. What is my logic 1? Well, it's VDD. How much noise can I add and still this will be VDD and 0? Well, you can see from your VTC, I can add up to V inverter. And then still this input can become V inverter and V inverter, or a little less than V inverter, and this is still VDD and 0, still working like the normal logical values here. Because VDD is for us, logic 1, 0 is for us, logic 0 here. So there's no ambiguity, straightforward how to define noise margins. And similarly here we can define what is the noise margin for the higher side. There's no problem with this in an abrupt characteristic like this. But what about here? How do I define noise margin? Okay, again, this is what I'm interested in, that logically my circuit should work fine. See, inverter is a logical unit. I'm not really interested in what the voltages are. As long as you can say, well, if this is logic 0 and this is logic 1 and this is logic 0 and this is logic 1, is fine. Whatever value you want to assign to 0 is fine. Whatever value you want to assign to 1, okay, doesn't matter. But it should be consistent. That whatever values you assign to 0, same values are here, everywhere. And as long as you're consistent, it doesn't matter. Right? So logical correctness is what I'm looking for. Now, in this case, what would you say is 0? And what would you say is 1? I have to map these logical values to voltage levels. What will you call? What is 0? And what is 1? Will you say 1 is still VDD? It seems a choice, reasonable choice. What if I call 1, logical 1 means the voltage has to be VDD. Suppose I say that. Logical 0 has to be 0 volt ground. And logical 1 has to be VDD. And then logical 0 is 0. How much noise can I add? Look at the system and still get a proper, what do I want here? VDD. Because what do you want? Logical 1. And we said logical 1 is what? VDD. Only one voltage we define. Logical 1 means VDD. So you want VDD here and you want 0 here. How much noise you can add? If I add 0.1, what will happen? This will become less than VDD. Look at your diagram. And this will become less than, greater than 0. Is it 1 and 0? Not according to our definition. Our definition was what? Logical 0 is 0 volt. Logical 1 is VDD. In that case, I don't have any noise immunity if I define it like this. Okay, same in this case. I don't have noise immunity. So, but you can see that my inverter does have noise immunity. There's a gain less than 1 and all that. It does have. It's just that I'm not defining it properly. It's not correct to say that logical 0 only means 0 volt and logical 1 means only VDD. That's not correct. You know that VDD is logical 1. If this is 3.3 is logical 1. 3.2 is also logical 1. 3.1 is also logical 1. Right? Why should you only say 3.3 only I will consider as logical 1 and everything else is not 1? Right? Then the whole thing becomes a indeterminate region here. At this point you have 1 and at this point you have 0 and that's it. And all other regions is indeterminate. So you're saying that this is not proper. But then what would you define as 0? Or what would you define as VDD? So 3.3 is VDD. How low should I go and say still it will be considered as logical 1? So you are obviously saying if 3.3 is logical 1, 3.2 is also logical 1. Okay, 3.1 is also logical 1. What about 2.9, 2.8, 2.7? What about 2 volt? Would you still consider it as logical 1? 2 volt would you consider as logical 1 or not? If the signal is above 2 volt, will I say it's logical 1? How do I decide? How do I decide what region to consider as logical 1 and what region to consider as logical 0? That's the problem that we are addressing. Okay? So, need proper definition of logic levels in terms of voltages. Now, how should you define what is your goal? Your goal is that you want to map these logical values to voltages such that you map it in such a way that your noise margins are maximized. We need a definition of logic 0 and logic 1 such that the noise margins are as large as possible. Okay? So let's look at our system here. So this is what we are looking for, logical correctness. Logically it should work correct, and we have to map logical 0 and logical 1 to some levels here. So I have a 1 level VDD and 1 level ground. And we know that simply calling this as logic 1 and logic 0 is not sense here. Maybe what I should call is a band of voltages here as logic 1 and another band which we should call it as logic 0. Anything which lies within this will be interpreted as logic 0. Anything which lies within this will be interpreted as logic 1. Now the issue is how large. How far should I dip in and how far should this go up? And still I can call it as logic 1 and logic 0. Okay? So let's come back. So we see that we need a band, a range of voltages that I will consider as 1, a range of voltages which I'll consider 0 here. So look at this one. This is what I will consider as 1. Let's say this is what I consider as 0. So what we are saying is the following. Any voltage which lies between VOH to VDD we'll consider as 1. So we define a level VOH. VOH is what? Is the minimum voltage that my system must have to be interpreted as 1, logical 1. So anything which lies between VOH to VDD will be considered as 1. That's the meaning of VOH. Anything which lies less than VOL will be considered as 0. Right? So we are introducing two levels here now. VDD and ground, of course, we know. So VOH and VOL we are introducing. Now note that VOH corresponds to a voltage called VIL. Let's call this voltage VIL. Why are we calling VIL? Well, I can apply a voltage. Note that in an inverter, normally the voltage may be 0. You're applying 0 volt here. But it says I can apply up to VIL as an input to the inverter. And the output would be what? A valid one. I can apply less than VIL, of course it's a valid one. But I can go right up to VIL and still get a valid logic 1. So that's the meaning of VIL. And similarly, I can define a voltage VIH. It says I can apply a voltage as less than this thing to get a logic 0 here. If I apply more than VIH, of course I get a logic 0 here. But I can go up to VIH and still get a logic 0 here. So we get these 4 VOH, VOL, and corresponding to VOH, we get a VIL. Corresponding to VOL, we get a VIH. Right? But right now, we have not addressed the issue of how wide should this band be, how wide this band should be. What we are saying is, we define a range of voltages as logic 1, a range of voltages as logic 0. And then once you do that, you get a VOH and you get a VIL, and you get a VOL and you get a VIH. All right. So if you define it like this, what would your noise margin be? Now note, under worst case scenario, what would, 0, 1, 0, these are logical values. Under worst case scenario, what would your 0 be? If according to your definition, worst case value of 0 is VOL. Worst case value of 0 is VOL. Because VOL, anything from here to here is considered as 0. So worst case value of 0 is VOL. So let's put VOL here. Now how much noise can I add such that logically things would be fine? How much noise can I add here? NML. Because we are talking about noise being added to the low side here. So how much noise can I add such that logically these should be fine? Now note that for logically 1 should be fine. This is VOH. At least it should be VOH. And to get VOH, what do I need? To get VOH, I need VIL. So the maximum noise that I can add here will take it up to VIL. And this VIL will still give me a valid output voltage here. It still can be interpreted as 1. And therefore, my noise margin on the lower side is VIL minus VOL. According to my definition, this much noise I can add here and the system would work fine. Right? System would work fine. VIL minus VOL. Same thing I can do with this one. Along the same side here, 1, 0, 1, 0 here. The worst case value of 1 possible is VOH. And I still want a valid 0. Well, valid 0 can be, so how much noise do I add here? So VOL here. And to get VOL, I need a VIH here. So VOH minus VIH gives us NMH. So we get the noise margins. NMH is VOH minus VIH. So according to my definition, if I define my logic 1 like this and logic 0 like this, the noise margins are VOH minus VIH and noise margin on the lower side is VIL minus VOL. So far, it's only definitions, right? These definitions make sense. Now, if you're thinking, I've added noise only to one side, one input. If I add noise to everything, will my system still work? These much amount of noise, NML and MNH? Well, the answer is yes. All right, so you can see here. Let's take this one here. Let's take here. So let's add noise everywhere. NML and MNH here. I add noise NML here, NMH here, NML here. So let's say this is VOL. You can see here this becomes VIL. This becomes VOH. Add the noise here. This becomes VIH. You can see it works fine. It's still a valid logic 1 and logic 0. So you can add noise to every input, and things will work fine according to our definition here. So under worst case scenario, if I define NML and NMH like this here, under worst case scenario where every input has a noise of equal to NML or noise of NMH, still my output values are fine. Okay, so these are definitions. Now the issue is again, how large should I make this? How large should this band be? How large should this band be? Okay, so the idea is, note that NML is VIL minus VOL and NMH is VOH minus VIH. Now I should choose my definitions. The point is, what is my VOH and what is my VOL? I should choose it in such a way that the noise margins are maximized. I should define my VOH and VOL such that the noise margins are maximum. So how do I do that? Well, one way that people do is as follows. Look at this V out versus V in characteristics. So note that we want to look at VIL minus VOL and VOH minus VIH. So one way that people do is V out versus V in, the VTC curve is given here. Draw another VTC curve. Draw another VTC curve, but it is sort of flipped. You take this as V out and this is V in now. Okay, so one V out versus V in, of course the black curve is there. Now suppose we call this axis as V out and this axis as V in. Right? So draw another VTC, same VTC curve, but with this being a y-axis and this being x-axis. I've not drawn properly, but you'll get like this. Okay? The red one is for this axis being interpreted as V out and this axis being interpreted as V in. Alright? Fine, so you get this red graph here, and the black one is for this being V out and this V in. So you get these two. Now, remember what our task is. We have to define what is VOH and what is VOL. So let's say I choose a point here. Note that VOH would be some point on this graph. This axis is VOH. So suppose this is VOH. I choose this as VOH. Okay, any point. Right now we don't know what it is. Choose this point as VOH here. So this is VOH. And the other choice that I have is, where is your VOL? These are the two things that you have to choose. What is your VOH and what is your VOL? Because once you choose VOH, it defines VIL. Once you choose VOL, it defines VIH. You don't have a choice there. You have a choice only in terms of what is VOH and what is VOL. That's it. The other things get decided by the VTC, voltage transfer characteristic. So suppose this is VOH here. And suppose this is VOL. On this graph, I define VOL. Note that for the red graph, this axis is V out. This axis is V out. And on the red graph, I say that this is VOL. Okay? So on the black graph, I define VOH. On the red one, I define VOL. Alright, no problem. Okay? Now, everybody sees that this point will be VIL according to our definition. VIL is on the black axis, right? VIL here. This is VIL. And this one will be equal to VIH. What corresponds? This is the input axis here. So this is VIH. Okay? Alright. Now let's connect them up. Let's make a box like this here. This rectangular box here. What is this this dimension here? NML. NML is what? VIL minus V0L. So this is NML. VIL minus V0L. And what is this side here? NMH. NMH here. So what are we saying here? What we are saying is go back here. What we are saying is the following. You have your VTC. You have your VTC. Draw another VTC with this flipped, V out and V in. Flip it here like this, right? Right now it's arbitrary. Define your VOH and define your VOL. And once you do that, these values get defined. Make this box here. Then what we are saying is this is NML and this is NMH. What is your goal now? How should I choose this point and this point? What is your goal? Goal is to make NML as large as possible, NMH as large as possible, and NML equal to NMH. So when you make NML equal to NMH, what are you talking about? A square. You're talking about a square, right? The two sides are the same. NML equal to NMH means a square. And so what is your goal of, what are you trying to find? These 2 points you're trying to find in such a way that you can find the biggest square that can be accommodated here. What is the largest square that you can fit in there? Right? So you draw these 2 graphs here and find out the largest square that you can fit in. Once you find that largest square that can fit in, that will give you the proper values of VOH and VOL. Your noise margins are maximized. So they say that is the way to define VOH and VOL. VOH and VOL, and therefore you'll get VIH and VIL obviously, and then you'll get the noise margins and all. So from any given VTC, what you do is you draw another VTC which is flipped here, try to fit the largest box in this particular one, and that will give you the largest box, which means make it a square. Try and make it a square, and you'll get the proper values here. So that's one way of finding out what are my noise margins. What are my noise margins? What is my appropriate value of VOH? What is my appropriate value of VOL? And what are the noise margins in my system? That's one way of finding it out. Okay, but you can see drawing another one, the second one, trying to find a square box which is of the maximum area that can be fitted. It's not very convenient. Not very convenient. So there's an alternative way that people try and find it out. Okay, the alternative way is here. What they do is the following, and we'll see why this makes, and the 2 definitions are close to each other also. The alternative definition, what they say is the following. They say this is my VTC. Find a point where the slope is equal to -1. Find a point where the slope is -1. That is your point which is VOH. And this is VIL. Find the next point where the slope is again -1. That is your VOL, and this is VIH. So these people say once you have a VTC, you find these unity slope points here. And these unity slope points will give you VOH and VOL. And then you get VIH and VIL, and then you find out your noise margins. So that's the other point that they're saying. Now the issue is, why are they saying -1? Why should you define it here? Of course, their goal is also what? All of them are trying to define the VOH and VOL with the intent of maximizing the noise margin. So we saw here, this is right. The maximum size square that you can accommodate here will give you the highest noise margin. So there's nothing wrong with this approach. This is perfectly fine. It comes from a definition of what is NML and what is NMH. And this is fine here. Why are they saying -1? So one has to prove that, so what we are talking about, you have to take a band of a range of voltages here. And we said, how low can I go to VOH? Well, they said, you should go to VOH as low as to a point where the slope is -1. If you go beyond that, they say noise margin will begin to decrease. So for example, if I start with VOH very close to VDD, noise margins will be low. As I start to decrease VOH, noise margins will increase. They will keep on increasing till I reach this particular point. If I go beyond this particular point, noise margin will start to decrease. So according to their claim, this is the place where noise margins are maximized. And if the claim is true, then the 2 methods will give us the same values. They should give us the same values, because this is also trying to find the maximum NMH and ML. This is also trying to do the same thing. Okay. So why to the point, why this -1 here? Okay. So let's look at that issue here. All right. So let's take this case here, where my definition of VOH is equal to VDD. So if VOH is equal to VDD and VOL is equal to 0, what is the noise margin? Let's start with an extreme case. VOH is equal to VDD. If VOH is equal to VDD, what is VIL? VIL is 0. And what is V0L equal to ground? 0, 0 minus 0, so you get 0. And this also is 0. So you start with 0 noise margin. Right? If you choose VOH equal to VDD and you choose VOL equal to ground, you start with 0 noise margin. Let's try to increase. So both noise margins are very small or 0. So let's try to reduce VOH. VOH was equal to VDD, let's decrease it. And let's assume for the time moment that these are symmetrical characteristics. It doesn't look symmetrical, but let's say this is symmetrical characteristics. So what I'm going to do is decrease VOH and increase VOL. So I'm going to expand this definition of logic 0 and expand this definition of logic 1 here. So I'm going to decrease VOH and increase VOL. What would happen? What will happen to VIL? If you decrease VOH, VOH becomes like this here. What happens to VIL? VOH you decreased and VOL also you increase by the same amount because it's symmetrical. Okay, so let's say I decrease VOH by 0.1. I increase VOL by 0.1. Okay, symmetrical. What happens to VIL? VIL goes here. Because note that these regions are, let's say, gain less than 1. Del V out by del V in is less than 1. And which means del V in by del V out is greater than 1. So what happens is, you increase this by 0.1. But the change in VIL is much larger. Why? Because you are in a region del Vi by del V out which is greater than 1. So VIL goes here. And what happens to the noise margin? Increases. Because you are in a region which is gain less than 1. Or del V in by del V out is greater than 1. So any small change in V out results in a large change in V in. So yes, you increased VOL, but VIL increased even more. And noise margin increased. So up to what point can you keep on doing this? Well, you can say increase it even more. Well, this will also increase. This will increase even more than this. Noise margin will further increase. At what point can you keep on increasing? Can you all see that this will stop when the gain in this, wherever you reach, the gain becomes equal to 1. You can keep on increasing keep on decreasing VOH or keep on increasing VOL till you reach a point where the gain is equal to 1. Because this is the basis for why noise margin is increasing. Alright, okay, let's do it with a little bit quantitatively. So NML is VIL minus VOL. So what we are saying is, let's increase VOL by, keep in mind that it's symmetrical. Both characteristics are symmetrical. So what we are saying is, we are at a certain stage where we have some NML and NMH. Increase VOL. You know, VOL is, we are still not at the maximum point. Increase VOL by a certain amount. Well, you're going to decrease VOH by the same amount. Fine. And as a result of which, there would be a change in VIL and there would be a change in VIH. So what will be the change in NML? Change in NML would be change in VIL minus change in VOL. Fine. Delta VIL minus delta VOL. We can take this out and write it like this here. Okay. So what does it say? How much would the change in lower noise margin occur as a result of change in your increasing VOL by a certain amount? That's what it is giving us. I can rewrite this as follows here. A change in NML due to a change in VOL. 1 by, now note why did I, so it should have been del VOL by del VIL, but del VIL is same as minus del VIH here. So we've written like this. So note that as long as is less than 1, NML will keep on improving. As long as this is less than 1, any change in delta VOL will cause a change in NML here. But the moment this becomes equal to 1 here, an improvement in NML will stop. Alright. So that's why this point here, what we say is that you can keep on doing it till you hit a point where the slope is equal to minus 1. And at that point, noise margin will no longer increase. noise margin will stop increasing. All right, so this brings us to our definition here. How do I define VIL? So you're seeing, why do I define it as slope equal to -1 here, and why do I define it slope equal to this thing here? So this is our definition of VIL and VIH, the place where slope is -1. There's one other complication. Many books, what they do is, so this is VIL minus VOL, and NMH is VOH minus VH. Many books will do what? They'll define NML as VIL minus 0 and NMH as VDD minus VH. They don't define. These are the proper definitions, by the way. Note. These are the right definitions of VIL, VOL, VOH, VIH here, and this is how you find them out. But at many books, and to some extent we'll also be doing it because, it's a matter of convention. If a lot of people are doing it. So NML, for example, you will see this definition in many books. NML is not VIL minus VOL. They define it like this, VIL minus 0. 0 is your stable logic value. And NMH is VDD minus VIH. Now, why are they doing it? Just 2 minutes I'll take. Look at this situation here. Why are they thing? If you according to these definitions, we saw that you can put noise on every input. You can put noise on every input and the system still works correctly with this. Maybe that's a very worst case scenario. It probably maybe doesn't happen that there's a noise on every particular one and the noise is NML, NMH, NML, NMH and all that. What these guys are doing is they're saying normally when there's no noise, I have 0, VDD, 0. These are the things that are happening in my system when I don't have any noise in my system. Now they're saying, how much noise can I add here when it's like this here, when it's normally 0? Well, I can add a noise equal to NML according to this definition because I'll get VIL here and I get again a proper value of VOH. Does it make sense what they're saying? But note that they're assuming it's 0 VDD. They're not assuming there's a noise here. They're not assuming there's a noise here. If they assume noise at every places, this definition goes wrong. It will not work. But if you assume that, most of the time is noise free, one of the place where noise gets injected here, well, then this definition is fine. So you get VOH here, you get less than, eventually the system will recover and you will get VDD here. Then they say, well, system recovers and so noise is a rare event. Again, how much noise can I add and still things work fine? So they will use this definition because then you'll get VIH and you'll get proper values. So this is the, if you want, this is the rigorous way of defining noise margin, NML and NMH like this. This is also very common that people, they calculate VIL and VIH like this, but they define it as VIL minus 0 and they define it as VDD minus VIH. Okay, so let's stop here. Next time we'll look at the examples.